Lab 4, Macroscopic View of DC and RC Circuits. The purpose of this lab was to predict the behavior of circuits with resistors in series and in parallel. We use ammeters and voltmeters to measure the current and potential differences across different parts of the circuit. We use this lab as an opportunity to learn more about resistors and capacitors. Throughout this lab, I found that the direction of an ammeter does not change the sign of its reading, but a voltmeter measurement does change with how its probes are oriented. All of the potential differences across the circuit added up to a total potential difference of 0, as expected. Another finding was that when a battery charges a capacitor and then is disconnected, the capacitor begins to discharge, and it will charge and discharge faster when run through a lower resistance light bulb. Finally, I compared my initial expected value to that calculated by a graph of data from the experiment and found that the time constant for this circuit was approximately 6 seconds. In this lab, we had to use and further develop our knowledge of series and parallel circuits and apply it to an online simulation. We used the principles of energy conservation, the loop rule, and principles of current conservation by creating a steady-state circuit. This online PhET simulation was able to mimic and improve upon a real-life circuit. This program allowed us to experiment without any imperfections and therefore gave us a more accurate and desirable outcome for each parts of the lab. In the beginning of this lab, we started with a simple circuit and predicted the currents at different points. My calculations showed that I got a value of 0.0204 amps, and the simulation measured 0.02 amps. This shows that my predicted value was in fact correct. The next part of the procedure involved using the voltmeter to measure the potential difference across all different parts of the circuit. Everything except the two resistors and across the batteries had a potential difference of 0, as seen in the bottom left photo. The first resistor had a potential difference of 0.959 volts. The second resistor had a potential difference of 2.041 volts, and the batteries had a potential difference of -3 volts. All in all, this created a total potential difference of 0 across the entire circuit. In the graph on the right, potential difference versus position around the circuit is represented relative to the negative ends of the battery. We then used our experimental potential differences to see how accurately we ran the experiment. The 47 ohm resistor was found to be approximately 47.95 ohms. The 100 ohm resistor was calculated to be around 102.05 ohms, and both the wire and the ammeter were both ideal and had 0 ohms. The differences in the calculated from expected values of 47 and 100 ohms is most likely due to the fact that the ammeter and voltmeter only measured to about 2 or 3 decimal places. In the final part of the lab, we observed how a capacitor charges and discharges when set in a series circuit with 10, 20, and 30 ohm light bulb resistors. This charging and discharging process occurred faster in lower resistances and slower in higher resistance light bulbs. We then plotted a ln of delta V over delta V naught versus time graph to calculate the RC constant. This graph shows my times and measured potential differences across the capacitor in the first two columns as it discharged. It also shows how I then divided each potential difference by the original of 9 volts and then took the natural log of this fraction. I graphed this natural log value versus time to get an approximate equation of y equals negative 0.1813x plus 0.242. This allowed me to solve for RC, which I got to be approximately 5.5157 seconds, which rounds up to my initially expected value of 6 seconds based on the 30 ohm resistance and 0.2 farad capacitance. A real-life ammeter is not as ideal or perfect as the ammeter used in this simulation, and it would have had some internal resistance. This would have caused the current and potential difference to change slightly across the ammeter, which we didn't observe with the use of the ideal simulation. Again, a real-life battery is not as perfect as the ones used in this lab. The capacitors would have charged much slower than the 9 to 10 seconds we saw through the 10 and 20 ohm resistors. This lab allowed us to use a computer simulation to create a more perfect representation of both DC and RC circuits. We found that the time constant RC for this particular circuit was 6 seconds, according to both the original calculations and data taken from the experiment. This lab allowed us to use both the energy conservation loop rule, and we were able to keep the circuit in a current conserving steady state.